high jump. I'm Jessica and this is Kayleen.
So the reason we chose this topic to base our calc project on is because we both participate in high jump and we thought there was a lot of calculus in high jump.
Is everybody supposed to jump? Okay, so to start off, we'll talk about the history of high jump. So men's high jump was introduced to the Summer Olympics in 1896, and women's was introduced in 1928, and it was actually the only jumping event available to women until 1948, so there was no long jump or triple. And jumper's technique involves scissor kicks and straddle kicks, but since 1968, the Fosbury flop was popularized and perfected to be the regulated jump, so it means you have to do the Fosbury flop. And the rules of high jump, you have to jump off of 1 foot, and then it's a failure if the bar is dislodged from the standard, and this is a standard. And you get 3 attempts at one height, and 3 consecutive misses, you get eliminated. You get to skip heights if you're a really good jumper instead of starting at a low height. And then a tiebreaker to find the victor, you go off a few misses.
So like skipping height, sometimes the starting height is like really low, and so like Jess would skip heights because she doesn't want to waste her jumps on like the lower heights.
So this is a video of Fosbury flop.
On the video. Right there.
But never excelled at anything until at the In the early 1960s, Dick Fosbury tried his hand at almost every sport, but never excelled at anything until, at the age of 16, he turned to the high jump. But when he couldn't compete against the strong athletes at his college, using the standard high jump techniques at the time, Fosbury tried to jump a different way, backwards. Instead of jumping with his face towards the bar, bringing each leg over in the traditional straddle method, he jumped with his back towards the bar. Fosbury improved his record by over half a foot and left his coaches amazed by this strange new style of high jumping. During the next few years, Fosbury perfected his high jump style, won the U.S. national trials, and assured his place in the 1968 Olympics in Mexico. In the Olympic Games, Fosbury amazed the world with his new technique, winning a gold medal with an Olympic record leap of 2.24 meters. By the next Olympic Games, almost all the competing high jumpers had adopted what came to be known as the Fosbury flop. What's the secret behind the technique? It lies in a physics concept called the center of mass. For every object, we can locate the average position of all of its mass by taking into account how the mass is spread around the object. For instance, the center of mass of a flat rectangular object of uniform density will be in the intersection of both diagonals, in equal distance from each corner. We can find the center of mass for other objects by similar calculations, or by finding the object's balancing point, which lies right underneath its center of mass. Try balancing a broom by holding it and slowly bringing your hands together until they meet. This balancing point lies right underneath the broom's center of mass. We humans also have a center of mass. When most people stand up, their center of mass is around the belly. But what happens to your center of mass when you lift your hands in the air? Your center of mass moves upwards. It moves all the time as you move through the day, based on how your body is positioned. It can even move outside of your body. When you bend forward, your center of mass is located below your bent belly, in a place where there is no mass at all. Weird to think about, but that's the average position of all your mass. Many objects' center of mass are outside their bodies. Think of donuts or boomerangs. Now look at the Fosbury flop and follow the position of the center of mass of the jumper. The jumper runs very fast, so he can divert his horizontal velocity to vertical velocity, and jumps. Wait for it. There. jumper's center of mass as his body bends backward. It's below the bar. That is the secret behind the jump. With the old pre-Fosbury techniques, the jumper had to apply enough force to lift his center of mass above the bar by a few inches in order to clear it. The Fosbury flopper doesn't have to do that. The genius of the Fosbury flop is that the jumper can apply the same amount of force but raise his body much higher than before. That means he can raise the bar so high that even when his center of mass can't go any higher, his arcing body can. Fosbury's technique brought the high jump to new heights by splitting the jumper's body away from his center of mass, giving it that much more room to clear higher and higher bars. So the Fosbury flop may be sports history's only great leap forward that is also a great leap backward.
We decided to show that video to explain what center of mass was because we talked about it a lot through the presentation. So the key differences between the straddle and the Fosbury is that the straddle, you go over the bar with your stomach, you run straight up, you have a lot of double arm motion, and then you have a straight lead leg and a fast run up. And for Fosbury, you clear the bar with your back, you have a curved run up, you have weaker arm motion, you have a bent lead leg, and you have an even faster run up. And so we found out that you have a bar clearance greater of 3 inches and a disadvantage of 2 inches compared to the straddle, which is a 1 inch difference, so that makes the Fosbury better. Our first calculation we decided to do on my jump curve, which is my center of mass going over the bar.
So to find this calculation, we used Capstone, which is like a program on our computers where you can use a video and then plot all the points you can like plot points on the center of mass as the video plays. And so we use this to plot all the points of our center of mass and then find a line of best fit. And then we use that line of best fit in order to create an integral to find the area under the curve, which is the area between her back and the bar. So this was the equation that we got from using the line of best fit, and then we integrated it from 0 to 1.75 because that's where like she ended on the mat, and then we got an answer of 0.887 feet. So that seemed like really small, so we decided to check our answer to make sure it was actually accurate and we didn't make a mistake. So we used a triangle inside the graph of best fit, and so we found the area of the triangle, which was 0.56 feet, and since obviously it doesn't encompass the total area of the curve, it was going to be an under approximation, but since it was close, we decided that our answer is accurate.
And then we decided to do the arc length, which is my center of mass going over the bar, so it's pretty much like my back length. And so we used the equation from the previous slide, and then we took the derivative of it, and we put it into the arc length formula and got 3.255 feet.
So then our next calculations were on the curve that she runs, which is just like her approach basically. And so we wanted to find the actual area under that curve, and so to do that we actually went to the track and drew out what she runs and then found like 6 points along it, so we could plug that into our calculator to get a line of best fit, so then we could use an integral to find the area. And so we plotted points at 5, 8, 11, 14, 17, and 20, and then plugged those into our calculators and got this equation for the line of best fit, and then did from 5 to 20 since this is 0, so that starts at 5, and got an answer of 404.174 feet for the actual area underneath that. after we found the actual area using an integral, we wanted to figure out which one of the four methods to approximate area would give us the closest answer to the actual area, so we used four different methods. So the first method we used was geometric approximation. So we put shapes inside and tried to fit them best to the actual shape of it. And so we found the area of the triangle using height times length and then dividing by 2. And we got 101.25 feet. And then the square we got 262.5 feet for a total of 362.75 feet. And this is obviously an under approximation since the shapes don't fully cover the area.
Next we use left rhyme and sum. So then we have all the ordered pairs. And then it was 423 feet, which is an overestimate because the graph is decreasing concave down and left rhyme and sum is. And then we used right rhyme and sum. And we got 382.5 feet. This was an underestimate because the graph is decreasing concave down and right rhyme and sum is used. Lastly, we use trapezoidal rule. So it's an underestimate because the graph is decreasing, but it ended up being our closest approximation, which ended up being 402.75 feet.
Which was only like 2 feet off of the actual area, so it's a good approximation if you can't find the actual area.
And then we decided we wanted to find out how far I ran during my approach. So we used the distance formula of the points 5, 31, and 28, 0. And so then we took that, but then we realized it was going to approximate that line. And we got 33.541 feet. And we thought that that wasn't a very good or accurate answer. So then we did the distance. Oh yeah, sure. This is just the running distance. So then we did the distance formula between each pair and added them together. So then we got 38.819 feet, which we think is more accurate of an answer that I ran.
Okay, so next we wanted to find the equation of the tangent line at the point where she actually starts curving, because for high jump you run straight for 4 or 5 steps and then start to curve in towards the bar. And so we wanted to find the tangent line at that point. And so we used a function that we got previously when we found the area, and we took the derivative and then plugged in the point 20 to get the slope, and the slope was negative 1.911 at that point, and then plug that into the equation for a tangent line, and you get that yt equals negative 1.911 x minus 20 plus 17.5, since 17.5 was the y value. So we wanted to find her velocity when she started her jump, like when she actually left the ground. But you can't just find the velocity because it's a diagonal motion. So you have to find the velocity in the x and then the velocity in the y first. So we used capstone again and made graphs of her distance over a time. And so this would be the distance, and then that's the time that it took her to do that. So we found the velocity by doing distance over time at that point, since it's not average velocity because it's only at one point, and it's 9.747 feet per second. And then her y, we did the same thing, and it was 4.903 feet per second. So then to find the overall like diagonal velocity, you have to do the Pythagorean theorem, and so it's just a squared plus b squared equals c squared. So we had to take the square root of a squared plus b squared, which was 119.043, which ends up giving you 10.911 feet per second. So that was her velocity when she left the ground. And then we wanted to find how high her center of mass went and what the highest point was. So we used this projectile motion function, but then we had to solve for time, we had to take the derivative to get it as a velocity function. So we took the derivative and then set it equal to 0 to solve for t, and then t ended up being 0.5 seconds. So 0.5 seconds after she jumps was when her center of mass was at its highest point. And so after we found the time, we plugged it back into this equation with the y velocity, because this is all in respect to y, because we're finding the highest point in the y. And so we ended up that her highest point was 4.727 feet. And then we looked at the graph we made, and it said that, like, what we calculated on the graph said it was 4.66 feet, which is like relatively close to our answer, which we could have just accidentally like plotted 1 point wrong or something, which would like skew what we had.
Finally, we did the angle of takeoff, which is the angle of my body as I planted my foot to jump. And so we used the velocity